This is going to look like a quadratic. So let's say we peak here, we go down forever this way, we go down forever that way. So, we go up and then we go down, okay? So this is a nice example of a quadratic equation. You don't have to know that. That's going to be actually in the next chapter. We're going to go over that a lot. But for now, the first topic in 2.1 actually talks about increasing, decreasing, and constant intervals on our graph, okay? So this is a function, right? It passes the vertical line test. But we've got to know where this thing is increasing and decreasing. And the visual way, I'm a visual learner, okay? So the visual way I do this is if you think of the graph as maybe like a roller coaster, and you've got someone on it. Now they've got to be going from left to right, okay? So if I drew a little guy on a roller coaster, and he's right there, now he's going left to right. At this point, or at this spot on the roller coaster, you would say he's increasing, right? You guys agree? And then what's happened, we're going to hit this vertex right there, and he's going to be decreasing afterwards, okay? So we have a switch. Sometimes math books call this a turning point, okay? We have a turning point. I'm going to use a different color marker here. Hopefully it shows up. If not, we tried, okay? But right here, can you guys see that? Yeah, we have a turning point, and that's what x equals 2. At x equals 2, we have a turning point. And we have two intervals going on, so I'm going to sit for a minute and talk about interval notation because that's what the 1.7 section is about that we haven't got to. So I'm gonna kind of treat this like you haven't seen interval notation before. But when we talk about increasing or decreasing intervals, we always use x values, okay? We always use the x values. And if you look at this, before 2, that green interval right there, you would say we're increasing, right? Right, we talked about that. So before 2, we're increasing. Boop, 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 boop. We're almost to the fun part of the roller coaster, right? And then after 2, you would say we're decreasing forever, right? We're decreasing, right? You guys agree with that? Makes sense. Now, we have to write these in interval notation. And interval notation just uses parentheses, brackets, and commas, okay? So the first thing I'm going to write is this interval for increasing. I'll keep the colors consistent. Ooh, maybe not. Hold on. That one I can barely see up here. So where are we increasing? Can you guys see that online? Like, is that big enough? We'll just say something if it's not. That's fine. Okay, we would say we're increasing from negative. Look, all I'm doing is following this green line. It's from negative infinity to 2. Okay? Now look, with infinities, we always use parentheses. So the interval is going to look like this: parentheses, negative infinity. And then it's going to stop at 2. Remember, at 2 is our turning point, right? 2, we switch and we go down. So it's going to switch to decreasing. So negative infinity to 2. Now, here's the thing with intervals, though. Look, you would never include a turning point because a turning point, a single point is not increasing or decreasing, okay? It's not increasing or decreasing. So because of that, it would always get a parentheses because we're not including it in the interval. If we included it in the interval, it would get a bracket, okay? It would get a bracket. So we're going to put a parentheses right there. This thing increases from negative infinity to 2, okay? Then at 2, we know it switches. We've got the turning point, right? So let's switch to blue. So we've got decreasing now. So decreasing, well, it switches at 2 to decreasing, right? And we go from 2 to infinity, okay? At 2, it switches, and we go to infinity. Notice, we're not using the y values. We're not going up to 3 here. It does go up to 3, right? The maximum, you could say, is 3 for this graph. But we're not worried about that. We just want to know, where is this thing increasing or decreasing, okay? Okay, so let's look at another one. And I'm going to ask you to tell me this. And I'll tell you, if it flatlines, it's constant. Okay, so let's do one that has all three. And I want you to decipher it, okay, to try it. So let's say we've got a graph. Whew. And let's say it does something like this. Let's say it goes to here. And then it flatlines a little bit. So remember that means constant. And then it goes down. Okay, so I'm asking, I want you to fill this in. Increasing, attempt it. Increasing, decreasing. And this one will have a constant. Okay, increasing, decreasing, constant. And remember, we're going to use this interval notation. And if you're not familiar with it yet, that's fine. That's why we're going over it. I'm going to go get a water. I'm going to be dehydrated. Keep working if you're working. It's no big deal. I'm just going to try to come in behind you here now. Look, where it switches from increasing to anything else or decreasing anything else, we're still going to consider that a turning point. Like our turning point was 2 here. Well, here we've got a turning point at -1, right? And then a turning point at 3, okay? And now we've got to think, well, what's happening in these intervals, right? This thing goes forever to the left and forever to the right. So therefore, we've got really 3 intervals going on. And I'll tell you the easy one's right here, in between here. That's definitely just a constant, right? It flatlines from -1 to 3. So again, I'm going to say -1 to 3. In parentheses, because just like before, we're not going to use the endpoints. We're not going to include them for this example, okay? But then I've got to decide what's happening on the other two intervals. And look, you got to be careful. That arrow is tricky, that one to the left, because it's pointed up. It looks like it's increasing there, right? But remember, we're going left to right. So really, if we think of our guy on here, riding the roller coaster, he's going down. And he's also going down here, right? So these 2 intervals actually are going to both be decreasing. Okay, so I'll use blue. So we've got 2 intervals here that are both decreasing. So I wanted to show you how to write that. And I know I did go over it. I should have gone over 2.1, but I'm going to show you how to write that here. So if we've got 2 separate intervals, we always start with the one furthest to the left, okay? So I'm going to start here. This interval would be -infinity, right, to -1. Okay, and again, I'm going to use a parentheses because we don't include the turning point. Now, if we have another interval, we're going to use this union symbol, okay? This union symbol means or. So what that means in mathematics is that we are decreasing in this interval or this interval. Now, for the other interval over here, eat my words, we go from 3 to infinity, okay? For the other interval, we go from 3 to infinity. Oh my Lord. What did I do wrong here?
freedom and infinity should be increasing.
Well, these should both be in decreasing. I wrote these in the wrong spot. Yeah, look, what's happening? What's our roller coaster guy doing? He's decreasing. He's not increasing. Yeah. Oh no, guys, I wrote this wrong. Here, look, I'm going to do a quick fix. That's decreasing. That's not it. They're both decreasing, right? The guy's going down on both of them. For this example, there's no increasing, right? If you think of riding the roller coaster left to right, he's never going up, or she, doesn't matter. They're never going up, okay? So because of that, we're just not increasing. I'm going to do a circle with a line through it. That means the null set means there's no solution there, okay?
On the negative infinity, because it looks like an endpoint, it's not a bracket. I mean, how is it at negative infinity? I'm confused. Shouldn't that just go on?
Well, yeah, and it's because this arrow is right there. You got me? So
Okay, I didn't see the arrow.
Yeah, and that's why. Is that Jeanette? Yeah. Yeah, it's so because the arrow goes from. Now you're right though. Let's do one more. We'll do one more, and I can include another kind of topic with this. Is well, what if it stops? Right? What if it stops? So any other questions about these two? I'll leave this one up here. I'm going to erase this one.
So they're always coming from the left to the right.
Yes, it's always
that line.
Yeah. There's like a weird math definition if you want to look into it. And it's in your book, and it's on like the bottom of page 230. And we can go into that if you want, but I'll tell you something. It's a lot easier to grasp if you think of the guy rolling left to right. Okay, so let's look at one that Jeanette kind of brought up a really good situation. What if it doesn't go forever to the left or right? Like what if let's say we start at 1, 3 here, right? We start at 1, 3, and then we dip down and then go back up. So let's say we dip down to like 2, 1, and then we go up forever. Now this low point right there is at 2, 1, and then now we do go forever here. Okay, we go forever here. Now I'm going to ask you the same thing again. I want you to fill it in. So increase. Hopefully I'll do this one correctly. Increasing, decreasing, constant. So for this one, where are we increasing, decreasing, or constant? Okay, try to fill that in, little quiz. Okay. If you're not done, that's fine. Let's talk about this one though. I'll use some other colors. So we'll do red. Right here, look, we're decreasing, right? If we go left to right, we're decreasing. So we're only decreasing from 1 to 2 here, right? That little interval is the only interval we're going to be decreasing. And then we have the turning point, right? And then it goes back up. So I'm just going to make that blue. So it goes back up forever. So our turning point though is at 2 right there. So now, Jeanette, even though that black dot means we include oh gosh, what am I trying to say? I'll do an example of this. That black dot would mean that the coordinate 1, 3 is included in the line. We'll do domain on this one in a second. It would be included. But for decreasing though, you would never include a coordinate because you need an interval. So for decreasing, we would go from just 1 to 2. Just 1 to 2, right? Boop, just right there. Okay. Remember, we're only using x values. That looks like a coordinate, right? But it's not, it's an interval. It's from x equals 1 to x equals 2. We're decreasing, right? And then at 2, for forever, we're going to be increasing. So 2 to infinity. And now the constant, this one doesn't have a constant again, right? We don't have a constant. Okay? Questions in Zoom land or in real land? No, you're good.
Question, I was just trying to remind myself that it's X.
I'll tell you, that's the most common mistake on this one. The common mistake is we see, oh wait, but we're decreasing from here to here, right? Because when we think of increase or decrease, it's up or down. So, but it's where it's happening, right? So if the question, and that's a good thing to bring up. If the question asks where something is happening, it's talking about X value. So we can write that down. If the question asks where, that's going to be an X value. And I'll tell you, that's almost specific to Blitzer, to this book. It's his terminology. He likes that. Okay, so where, but typically the what question is the Y value. And we'll see that here in a minute, actually. So if it asks where something is happening, it's the X value. What is, like, I'll tell you, for instance, we're going to talk about relative min and max. It'll say, what's the minimum? Or I'm sorry, where does the minimum occur? X equals 2. What is the minimum? Y equals 1. Okay, and we'll get to that. That's actually the next topic. But before we get there, I want to review something that's in that 2.1 lecture, and it's the domain and range of this graph. Okay, the domain and range of this graph. And remember, if you watch that video, and you're right, it's hard. I'm telling you, if I can make them like small videos, you know, and I would, me and the other math teacher were talking about that. Like, he's making an online class, a purely online one, and he's doing it that way. And it's like, oh, that would be so much easier. It's just hard to do in the lecture. You have to start something.
Oh, yeah.
So anyway, back to the domain question. Now remember, the domain are where our X values exist, right? And the range are where our Y values exist. So I'm going to erase this real fast, because now we're not talking about increasing or decreasing. We're just talking about where these things exist, right? And if we look at the x-axis, let's use blue here. Our x values start existing at 1, right? And then they go forever to the right, right? They go forever to the right. Now, look, I wanted to go over this for this specific reason, is for this example, you would include the 1, okay? Because it's a filled in circle here, you would include the 1. And if you include the endpoint, it's got to be a bracket, okay? If you include the endpoint, it has to be a bracket. So our domain for this question would be bracket 1 to infinity. Now, infinities always get parentheses. So if you went out and got an infinity tattoo on a whim in Destin when you're on vacation, you need to put a parentheses on it, okay? Because they always get parentheses. Okay, let me fix this one. Okay. Now, the reason we didn't include anything up here is because with intervals of increasing and decreasing, you never include endpoints. If I asked you, well, are we increasing or decreasing at x equals 1? Well, it's a coordinate. You're not increasing or decreasing on a coordinate. You need an interval for that, okay? So let's talk about the range now. The range is where the y values exist, right? We got the y values here. Well, if this thing goes all the way down to 1 as well, right? It dips down here at 1, and then it goes up forever. Turns out it's going to have the same exact range. I didn't mean for that to happen. It just happened, okay? So the range, same thing. It goes all the way down to 1. And then this arrow means it goes up forever. So we go 1 to infinity. Okay, kind of neat. Okay, questions? I'm like off the screen. This is where, if I'm lecturing in real life, this is where I like saying. But then I'm not on the screen. Okay, do you guys have any questions about the domain and range? Now, if you watch 2.1, I went over this, right? That was in this, I think, towards the end. Now, over here, I'm going to do the same thing. I'm going to ask you the domain and range. Just to follow up on that same concept from Tuesday. You try this one. Try this one, and then we'll go over it. Write down what you think it is. We'll see if it's right. Okay, let's just talk a minute about this. Keep writing if you're right. Comparing it to the previous one. Look, the domain, remember, this is where the x's exist, right? Well, this thing goes forever to the left and forever to the right, right? So therefore, now there's two ways to write this, I'll tell you. In your book, they use interval. So they'll do negative infinity to positive infinity, right? Now, if you want to shorthand this, there's nothing wrong in it, but I'll tell you, on the test, it'll probably be written this way, okay? Because this will be a multiple choice type question. It's a good multiple choice question. But a shorthand way to do this is you write it like that. Kind of looks like the indentation paragraph symbol, but it's an R instead of a P. And it means all real numbers, okay? All real numbers. We could plug in any x value on this line. We'll actually plug in any x value, and we'll get back a y value, okay? Over here, that's not true, right? If I chose like x equals -2, there's no y value to accompany it, right? That's why it's not in the domain, okay? But over here, that's not true. It goes forever. Same thing with the range, right? The y values. This thing goes forever down and then forever up. So negative infinity to positive infinity, okay? I know that was a 2.1 question, but I figured to kind of open up, if you guys have questions on it, it's a good way to open it up, okay?
So it's only written the way on the left side if it stops?
Yeah.
Okay.
Yeah, if it stops, either, by, bouncing kind of, or, changing, or if it just naturally stops right there.
Okay.
Yeah, that's how we're gonna have an endpoint. And we'll go over that a lot. I mean, this really will be, I say we go over it a lot. We'll see it in a lot of different ways too, Kelly.
Okay.
Okay, now let's go back to this one specifically, because I chose this one for a reason to go over the next topic, which is relative minimums and maximum. Now I'm going to kind of stick to the language your book uses here to keep it consistent. Yeah. So for this example, we're going to call that function f of x, okay? We're just going to give it a nice notation. It's f of x, right? And remember, if you watched that video, I went over how to do function notation. If you haven't watched the video, this function notation is going to look real weird. But come back to this point. Go watch that other part and then come back. But look, for this example, it has a relative minimum. Okay, to have a relative min or max, you have to be a turning point between increasing or decreasing. And it has to be just kind of like the highest number of all the numbers around it or the lowest number of all the numbers around it. And right here, we've got a relative max. I'm sorry, relative min, not a relative max. A relative minimum, okay? We have a relative minimum right there. And the reason is it's a turning point. It switches from decreasing to increasing, right? Now, I know what you're thinking, hopefully. You're kind of thinking, wait, well, is that not a relative maximum, right? And this is not a relative maximum because it doesn't switch. It just starts there, right? It just starts there. So we don't know what's going, actually nothing's happening to the left of it, but we don't know what's going on to the left of it. So it's not considered a relative max because it has to be that turning point, okay? It has to be a turning point to be a relative min or relative max. But I wanted to go over the verbiage of how your book goes over how to write the answer for relative min or max. And it's going to come back to the where and the what, okay? Yes. So the way your book's going to write this is f of x has a relative min at x equals 2, right? That's the where. F has a relative min at x equals 2, okay? And then the relative min is, so that's the what, f of 2 equals, well, f of 2, x equals 2, the y value would be 1. So this is how Dr. Blitzer that wrote your book likes to write it. It's just a long drawn out way of saying 1, 2, right? 1, 2, we have a relative min, okay? And I just want you to be prepared for that. So when x, oh, wait. It's 2, 1, isn't it? 2, 1, yeah, 2, 1. 2, 1 is the relative min. So this is just a long drawn out way of saying the relative minimum is 2, 1, okay? It's goofy. Now, this doesn't have a relative max because we don't go up and then down, okay? And we'll do an example of that hopefully here in a second. And you can see that it's on page 232. They did a different type example with like a trig function, but it kind of lays out how he likes writing them. Yeah, and even at the bottom of page 231 where he starts talking about it. Okay, great. Let me steal another example. We can go over like A, B, C, D, E, F, G on these. Okay, good, yeah. Let's look at, okay, let's do, I'm gonna steal an even one in your book. Holy cow, that's a lot of good stuff. Okay, let's do one more and then we can kind of, if you look at like, if you're in the book on 238, this is where I'm finding them. And let's do number, oh gosh, I don't like any of the ones at first. Okay, yeah, let's do number 2. Let's do number 2. And I'm going to ask more than they're asking for number 2. They just asked for what's the interval of increasing, decreasing, or constant. But I'm going to go over the relative max and relative min as well. I want you to give me that. Now, if you don't have the book at hand, this looks like a little quadratic equation or quadratic function, and it peaks at -1, 4. So -1 and then 1, 2, 3, 4. We're peaking right there. Crosses what at 3? -2 then. And where's it cross the x-axis? 1, -3. 1 and then looks something like this. Okay. It looks something like this. Well, infinity, but x. Okay, so I'm going to ask you a lot of questions about this one, okay? And we're going to start kind of from stuff yesterday. For A, I want you to answer what's the domain. For B, I want you to give me the range. For C, let's do the increasing. D, we'll do decreasing. A, B, C, D, E. And then we'll do constant. Okay, so domain, range, increasing, decreasing, constant. And then let's do A, B, C, D, E, F. Let's do if it has a relative min or max. So min or max, I want you to state it this way, okay? Relative min, it's kind of hard to write. Relative min or max, which one? And then I want you to state it in this manner. Gee, I'm going to ask you a few more things about this graph. I want the y-intercept. And I want the x-intercept, or intercepts, because there's 2 of them, okay? Yeah, okay, try that. I'll give you a minute. This stuff, I mean, there's not a lot of math involved. It's just pulling the information from the graph. Madeline, I'm just seeing your message, and I'll tell you, I can't, it's weird because when I'm lecturing, I can't see it. Were you talking about this? Which graph were you talking about, Madeline?
I think it was one of the first examples that we did like at the start of the lecture.
Okay, okay, I'm gonna tell you, just butt in. If you got a question like that, because I'll probably erase it as we're going along. So let me, at the end of class, I'll check it out. I'll answer you and show you where that lecture is.
Okay.
Yeah, guys, I'm telling you, the Zoom guys, don't feel like you're being rude, because it's hard to look at. It's really hard. I'm gonna tell you kind of how I'm seeing this from my eyes. I've got a few students in the class, which is great. I've got the lecture up here, and I've got the recorder here, and then the chat box is down lower. So it's just hard to keep up with all of it. So do not feel like you are being rude by butting in and asking a question. Okay, let's go over this. I'm going to start at the end, actually, the x-intercepts and y-intercepts. So look, guys, for x-intercepts and y-intercepts, we're going to write these as coordinates. So this actually crosses the line at two different places. The x-axis at 1, 0, right? We cross, and then at -3, 0. So at 1, 0, -3, 0, we have x-intercepts where our line crosses that x-axis. The y-intercept, we've got 1, right? It's right here. It's 0, 3. Okay? 0, 3. Okay. So now I'm going to go back to the front. I just want to fill that in first. A domain. Now, what's nice about this is, look, this goes forever to the left and forever to the right. I know it doesn't quite look like that, but this is going forever to the right and left. Okay? So for the domain, this is going to be -infinity to +infinity. I'll try to partition that out. Okay? The range, though, is not like that, right? The range does go forever down, but it stops going up, and it stops at 1, 2, 3, 4. It peaks right there at 4. So our range is going to be -infinity to +4. Now, look, that 4 is included in the range, so you're going to use a bracket. That 4 is included in the range, so you're going to use a bracket. And now I've got to answer the increasing, decreasing constants, so the earlier stuff. Now, look, if we're riding this thing, right? We're going up here, and then we switch at -1. So -infinity to -1, we're going to be increasing, right? Negative, remember, we use the x values. -1, and then at -1, we switch and we're decreasing forever. Okay?
That doesn't need a bracket.
It doesn't use, okay, infinities never get brackets, but the -1 does not get a bracket because with intervals. Okay, and I'm going to, a long answer to a short question. Okay? So the reason we wouldn't use a bracket here is if I asked you, let's get rid of this entire graph. Because it's a great question. And all we have is this singular coordinate. Okay? And I ask you, are we increasing or decreasing at that coordinate? Neither, right? So that's why we don't include it on the interval. Okay? Yeah, it's a great question. Okay? That's close enough. So now we don't have any constants, so I'm going to use that whole circle with a line through it. For no solution, then we don't flat line, right? We do have a relative maximum, right? We've got a relative, now I'm going to be a little lazy here, and I'm going to say relative max. Okay, but relative max at x equals -1, right? We got a relative max at x equals -1 that is, and now I didn't say this was f of x, but let's just say it's f of x. F of -1 equals, and it peaks at 4. We knew that from the range, right? It peaked at 4. So we've got a relative max at x equals -1 that is f of -1 equals 4. Okay, I really like this example because it encompasses so much that we've done over the last 2 lectures, okay? I'll tell you, the test isn't set up this way where it's like A, B, C, D, E, F, G because we're testing in Blackboard, but I'll tell you, all of this will be tested in some way, shape, or form on the test.
We can't see like the edge of the board where it says f of -1 equals.
Oh.
We can see what it equals.
Sorry.
It's okay.
No, you don't get that. You don't get that. If you're not in the class, yeah, hold on. Sorry, guys. F of -1 equals, what should it be? No, you guys can't. Yeah, you guys don't say. What should it be right here?
It'll be 4.
Yeah, it should be 4. Can you see that? Okay, good. Yeah. Please, good. Thank you for letting me know. Okay.
So you choose a relative min or max. You don't do both.
Well, it only has one, right?
Okay.
Remember, for relative min, it's got to go decreasing to increasing.
Okay. I
That's
was
a
trying
min.
to make it have both.
Oh, no, no,
I
no, no, no.
need it to.
Yeah, that really was like, is it relative min or max? Or maybe maybe it does have both.
It can have both.
Oh, we
Okay,
can
I
have both.
see.
Yeah. It can have
Okay.
both. Now, a singular min or max can't be both. Like singular point can't be both.
Yeah.
But a graph, and even if you look at that, like, look at that graph kind of towards the bottom on the page.
Yeah.
See that?
This one?
Yeah, that one's got both, right?
Okay, yeah.
Okay, great. So let's go on to the next, actually, I think it's the last concept in this section, which is great. Then we can kind of include it in it'll be IJ as we go on. The next is symmetry. Now, there's another topic your book goes over, but I'm going to stop here with symmetry. There's some authors that believe symmetry is the most important concept in all of mathematics that we should grasp. I think they're just kind of, I don't know why, but symmetry. I think it's all important. But symmetry is more of the visual, and we're going to see how it connects to the algebraic, to the formulaic aspect too. So symmetry, there's 2 types of symmetry with functions. The first type of symmetry is even. So we're going to talk about that first. Even symmetry. And I'm going to give you a nice, really basic example of even symmetry. Okay? A nice, really basic example of even symmetry. And it looks like this. Okay. It's going to be f of x equals x squared. We'll say x squared plus 1. Okay? X squared plus 1. And what I'm going to do is I'm going to plug in some x values to get y values. I'm going to do a table to show this. So we've got x and we've got y. Just to graph it. It's a really basic way to graph it, right? So if I put in like -2, and then I put it into the function, -2 squared is 4, plus 1 is 5. So -2, we're at 1, 2, 3, 4, 5. We're right here, right? At -1, we plug -1 in, we square it, we get a +1. We add it, we get 2. So we would get a +2. So -1, we're at +2. At 0, you plug 0 in, we just get back 1. Okay. At +1, +1, we plug that in. 1 squared is 1 plus 1, that's 2. So we get 2 again. Can you see that down there? Yeah. So at 1, we're at 2. And then at 2, we plug 2 in. 2 squared is 4 plus 1 is 5. So we get back 5. So we have a graph that looks something like this. Okay, something like that. It's not perfect because I'm graphing it as a human, but it looks something like that. So visually, we can see here that this graph is symmetric around the y-axis. Okay, so we'll write that down. Turns out even symmetry, it's always symmetric around y-axis. That's the visual part, okay? That's the visual part. So if we see a graph that's symmetric around the y-axis, boom, we know that it is has even symmetry, okay? Now the algebraic part comes from using the function notation. And it turns out if you pop in a negative x into the function, now if you watch that lecture from 2.1, we went over how you plug in like negative x and you get back values and things like that. Turns out when you plug in negative x to even functions, you get the same exact function back. Okay, you get the same exact function back. This mess comes early. This is like the cheapy, you know, the one back there.
Yeah.
It's all up in my glasses. Okay, so how do we show this? Well, let's look at this example and to show how this occurs. Well, if I plug in f, well, can you guys see that? Yeah, f of negative x to this function, I would get negative x squared plus 1, right? I'm just popping in negative x into the function. Well, what happens when you square anything? What happens to the negative? Turns positive. So you get x squared plus 1, right? Hey, look at this. It's the same thing. So you wind up with the original function. Kind of neat. So algebraically, if we have even symmetry, when you pop in the negative x, you wind up with the same exact function you started with. This will only happen if we're symmetric on the y-axis, okay? This will only happen if we're symmetric on the y-axis. Questions? No. Guys? Other than, yeah, I probably need to see another example of that. Okay? Let's look at another one that's not a nice, kind of polynomial. Polynomials is kind of easy to see the giveaway here. Even and even. Okay? That's the giveaway. Now, I'll tell you, that's not always true. We'll get to ones that are like even and odd here in a minute. But let's look at another one that's not exactly the same. Let's say we had, let's just do another example here. F of x equals the absolute value of x minus 3. Why not? The absolute value of x minus 3. And I'm going to ask you, the question is going to state, is this even, odd, which we'll go over here in a second, or neither? Well, I'll tell you, to find if something's even or odd, you do the same first step. You plug in negative x. This one will be even. So we're going to plug in negative x. And we get the absolute value of negative x minus 3, right? Well, what do we know about absolute values? Just like, it's like something like a warm blanket on a cold day. They can make everything positive, okay? Yeah. What's something else? What's something else that makes you feel positive? I don't know. Whatever.
My dog.
Your dog. Oh my God! But when the dog, when you wake up and then the dog sees you wake up and they're just as happy to see you that you are happy to see. Oh my God! That's the best. Yes, positive, right? So what happens though is when you take the absolute value of anything negative, it turns positive. So this is the same. This is the same as the same absolute value of x. These two are the same value. So what happened is we wind up with the original function. Okay? Now, I'll graph this one just for fun to show you. If you're going to graph this, it looks like a V. Absolute values look like V's. So it looks something like that. Okay? And it is symmetric around the x-axis. We're going to get into how to graph these actually at the beginning of the next chapter. Okay? So it's going to happen. We're just not there yet. Okay? So even functions, they'll call them even functions. They are symmetric on the x-axis, and when you plug in negative x, you get back the original function. Now, odd functions, say odd symmetry. Odd symmetry is a little different. Now, look, I'll tell you a quick tidbit about Mr. Shirley's lecturing career. The very first time that I lectured about this, I was 24 actually, and my head was like this big, and I'm like, I know all this stuff. I just came out of like this master's in mathematics, blah, 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 I'm smart person, blah, blah, blah. And I wasn't, of course. But I didn't prepare for this lecture, okay? Didn't prepare for this lecture. And I got in there and I went over even symmetry. And then I said, well, odd symmetry must be symmetric around the x-axis, right? Now I want you to visualize something that would be symmetric around the x-axis, just in your head. Visualize something that would be symmetric around the x-axis. And now remember, this section is titled More on Functions and Their Graphs. Why would odd functions not be symmetric around the x-axis?
Because you can't.
What do you mean?
It wouldn't be a graph, like it would just be like a straight line.
No, I mean, like, if we tilted this sideways,
Oh,
right? If we did something like this, it's symmetric around the x-axis, right?
oh, yeah.
Why would this not be an odd function? Zoom? On Zoom out there? Why would this not be an odd function? You know this already, especially if you watch 2.1 to the homework.
I did watch.
Is it because it's not a function?
Ooh, say it again.
That it's not a function?
It's not a function. Why is this not a function, Kinsey?
Because it'll have two repeating x's.
Yeah. If you drew like an imaginary vertical line, it crosses twice, right? It doesn't pass the vertical line test. That's another way to put it. Yeah, great. This is not a function. So 24-year-old Mr. Shirley is going on about odd functions being symmetric around the x-axis, and this like sweet person in the back raised their hand and said, you know, Mr. Shirley, the book says this is symmetric around the origin. And I learned a beautiful lesson that day that I still bring to class. Now, I've lectured this topic for a lot. I don't have to get to be as prepared, but definitely if it's a new topic, I prepare myself well. So it's actually symmetric around the origin. So I need to show you visually what that means. Symmetric around the origin. A very, very basic example of this, like x cubed. Let's do x cubed. F of x equals x cubed. And again, it's not a coincidence that it's cubed, it's called odd, okay? But x cubed looks like this. And this isn't perfect, but it looks something like this. Okay, for origin symmetry, you actually fold it twice. Okay, think about this. If I took this, these two axes and I fold the first one up here, it would go to like that, right? And then if I fold it across, no, it's not perfect. If I fold it across the y, then it would be the same graph, okay? So they're symmetric kind of diagonally. That's another way to think of it. They're symmetric diagonally. I'm trying to leave my nose up. I'm drag down. Okay, this is a good example visually of a graph that's symmetric around the origin. Another one might be maybe a neat looking one. I just don't know what the formula would look like or the equation, but if we had something like this. Ooh, something like that would also be symmetric around the origin. And notice you like kind of click it twice and it's the same graph. That would be symmetric around the origin as well. Okay, so let's go back to f of x equals x cubed. Now, look, if you plug in negative x, you don't get back the same function. You get back the negated function. You don't get back the same function. You get back the negated original function. So let's do that with the basic example of f of x. So if I plug in f of negative x here, I get negative x cubed. And now, look, the difference when you cube something compared to, say, squaring it, is it keeps its sign, right? So this winds up being negative x cubed. If it was squared, it would turn positive, right? But since it's an odd degree, it would turn negative. Okay? And then, look, the original function was x cubed. So what we have going on here actually is negative f of x. That's the original function, that's f of x, and it's negative on the outside. So this shows that we have an odd function. We plugged in negative x, and we got back negative f of x. Okay? Questions? I'm going to do one that's a little more complex now. So let's say we had g of x equals 2x to the fifth minus x cubed plus 7x. You guys can't see that, can you? Oh, you can barely see it. Shift it over a little bit. Can you see that one? That's 7x at the very end?
Yeah, we can see it.
Okay, there we go, plus 7x. It's a little better. Okay, so now, look, if I'm going to give you a function, and I'm going to ask you, is this even, odd, or neither? And the easiest way to do this is just plug in negative x. Now, I'm going to tell you this is going to be odd. I'm going to work it to show you how to visually see that it's odd. Okay, so when we plug in negative x, we get 2 times negative x to the fifth minus negative x to the third plus 7 times negative x, right? And again, what happens is all of these are going to keep their sign, right? They're all going to stay negative. So we wind up with actually, this would be negative 2x to the fifth, right? Because negative x to the fifth would be negative, and then you got a 2 outside, so it becomes negative 2x to the fifth. This negative and that negative make a positive, right? Only in math, 2 negatives make a positive. And then lastly, you've got minus 7x. Okay, the hint here, or the kind of the trick, is that every single term's signs changed. Look, if you go back to the original, first term was 2x to the fifth, now it's negative 2x to the fifth. Second term was negative x cubed, now it's x cubed. Last term was 7x, now it's negative 7x, right? If all, for this one, it's 3. If all 3 change, then it's odd. Now, algebraically to show that, you don't have to show it, but algebraically to show that, you would factor a negative out. If we factored a negative out of these 3 terms, we'd have 2x to the fifth minus x cubed plus 7x. We'd have the original function. Okay? Look, I don't know, I'll put an F there. That's a G. We plugged in negative x and we got back negative, we plugged in negative x and we got back negative g of x. Hey, it's an odd function. Okay, it's an odd function. Okay, question. So I'm going to give you this next one and I want you to tell me what it is. I want you to try this one on your own. We got like 2 minutes left. Okay, let's say we got h of x equals 2x squared minus x plus 3. So is it even, odd, or neither? I'm going to give you 1 minute. I'm looking at the clock. I'll give you 1 minute to try. This is the last topic. Okay, so I'm gonna plug in negative x, keep working if you're working. I'm gonna plug in negative x. I get 2 times negative x squared minus negative x plus 3. Well, we know when we square it, it turns positive, right? So the first one's gonna stay the same. It's just 2x squared. The second one though, negative, negative, that's a positive. Last one, of course, is a constant, so it doesn't change. So look, if I go through these, like, this is not even. Remember, even, that everything had to be the same, right? And the second one changed. So it's not even. It's not odd, because not all of them changed, right? If I factored out a negative, this would be negative 2x squared minus x minus 3. This is not the same as my original function. So this one is not even or odd. So it's going to be a neither or a neither, however you want to pronounce that. Okay? Okay, I've run out of time. There is one more concept I'm going to go over at the beginning of next lecture, which is the piecewise function section. So for now, for homework, it starts on page 238, section 2.2. I want you to start on number 1. Yeah. And go to 35. And then I'm going to skip over the piecewise function stuff. And I want you to, yeah. I want you to do there's an application which is kind of neat at the end. 83. '83 through 91. These are all going to be odd, guys. 83 through 91, and that'll be good. And then we'll go over the piecewise. The gap in here is on piecewise functions. We'll have to go over that next lecture. So this is all odd.